Okay, so some helpful review would be to go back to the very foundations of linear algebra. So that's why I'm doing this discussion 0, 1a, and 1b. So basically, 0 is not even introducing the concept of matrices yet. The very foundation of linear algebra is just, the goal is really to conveniently solve systems of equations. So for problem 1, we just have some solutions. Um, so I'll just quickly go through them since most of you should be familiar with this by now. This is just a review. So this one, 49x plus 7y equals 49, 42x plus 6y equals 42. You'll see that they're actually the same equation, just different scales. If you scale the second one by 7, 6, you'll get the same information, and if you subtract them from each other, you get 0 equals 0. This, of course, is a valid statement. Therefore, anything that satisfies one of these equations will, by default, satisfy the other equation. That means there's an infinite, like a straight line, basically, of solutions, if you look at it graphically. Now, for the second one, 5x plus 3y equals negative 21. 2x plus y equals negative 9. Well, this one is just more straightforward. So we try eliminating variables. There's also substitution as a technique, but in this class we're going to focus on elimination since we can standardize that, and then if we can create a standard algorithm for this process, then that is kind of like the next step, so that we can have a consistent way of solving the problem. So then if we turn this to negative, then this becomes negative 6x minus 3y equals 27. If you add them, the y's go away, which is the whole point, and then we have negative x equals 8, so x is negative 8 and y equals 7 if you plug it in to any of them. So for example, this is like y equals negative 9 minus 2x, which is 16 minus 9, which is 7. All right, so for the next one, it's very similar to the first one, except you'll notice the constants here are different, 60 and 30. Well, this one was made the same by multiplying by 7, 6. What happens if we multiply this by 7, 6 and subtract? Well, then we're going to get 0 equals 25. And we know this is a false statement, therefore both these conditions cannot both be simultaneously achieved. These equations cannot both be simultaneously solved. Therefore, there is no solution to this system, because for a system to be solved, both of them must be true. So the next one, now you're taking it up a notch. We're doing a system of 3 equations with 3 variables. This is still elimination. It just takes more time. So I like to eliminate this one. The first one can all be scaled by a factor of 2. I get no solution here. You could try this out. It's basically you do the same steps. You get 2y plus 2z equals 5 if you use this one as well. And that one. Not sure how. Okay, so yeah, you get y plus z equals negative 2, but 2y plus 2z equals 5 from the other equations, and then that's an inconsistent solution. But for this one, it's more consistent. We can have 2y plus 2z equals 2, and then we have y plus z equals 1, and then we get 0 equals 0, because these three, like, they're basically literally dependent is what we find, and that's an infinite amount of solutions. And for the last one, we just do this is what we call triangular. It's the easiest case because you can just use back substitution. So this is the easiest case because it only involves one variable, so z equals 2, then going back, y equals 1, and then x equals 1. All right, so those should be fairly mechanical. Hopefully everyone does not need too much review on that. Number 2 is a bit more interesting. So A is basically just the design. So I'll just go over the design really quickly. So if you have an air conditioning that can be off in the morning and then on in the afternoon, then in the morning is when you want to kind of, and then the TV can be on or off. Then in the morning is kind of when you want to isolate it. So you want everything off except for one variable. That's just isolating a variable. It's not even good for just linear algebra. It's good for all sorts of experiments where you want to isolate a variable and have others not be a factor. You're just controlling the other variables. So in this case, we wait for the morning when the air conditioner is off, but the refrigerator is always on, so we can have just the refrigerator measurement. And then in the afternoon, we can have refrigerator and air conditioning and all three. So that's basically triangular substitution like we did in the last problem. that problem. So for part B, I'm just going to write that out explicitly. So T1 is our first measurement. That's just the refrigerator. T2 is our second measurement, which is the air conditioner and the refrigerator. And T3 is all of them. So we can just directly back substitute. All right, so hopefully that was, this is the 0th discussion. So hopefully that was very straightforward to all of you, because that's just generally just an introduction into some more advanced concepts. So now we're going to deal with matrices. So if you have 2x plus y equals 6 and 3x minus 2y equals 2, then we can write it in matrix form just by caring only about the coefficients, as long as you have these in the right order, since this is always x and this is always y. And this is augmented so that we can treat these like equations, and then we can do elementary row operations, which are just basically algebraically valid operations for systems of equations. So these include scaling, adding, and replacing. We won't do too much replacing, since we're just going to try to keep everything in the triangular form that we're going to try to get. So this is 2, 1, 6, and this is 3, negative 2, 2. To get to this, you have to multiply by negative 3 halves here and add it. So that becomes 0 here. Negative 3 halves minus 2 is equal to negative 7 halves, and negative 3 halves times 6 is negative 9, plus 2 is negative 7. So that gets us to this stage. Now we eliminated that, but now we want to get this into like the direct form. So we want to scale it. Now we're going to scale by negative 2 over 7, so that's going to get this to 1, 2. So now we have 2, 1, 6, and 1, 2. So basically this is just back substitution. We have y equals 2, and then that means 2x plus y equals 6. That means 2x equals 4. And then if you do the back substitution, you subtract this row from that, which is what we're allowed to do. It's basically adding rows, except you scale this by negative 1 first. And that's going to get us to 2, 0, 4. And now we can just simply scale this all by 2, because we want to get this directly, x directly, not 2x. That's 1, 0, 2. And we can apply this very similar process to everything, including 3 variables, without much difficulty. So, as we can see, this is already eliminated if you set it up correctly, x, y, z, and then constant. Now, because that's already eliminated, we just, for sake of simplicity, eliminate this as well. So you multiply by negative 1 and add, and then you're going to get, so you're going to get negative 2 and then negative 1, which we just scaled. I skipped a step here, and I scaled to 0, 2, positive 1, because negative 1 scaled, and then negative 1 scaled as well. So then we scale that as well, and then we eliminate that by multiplying this by negative 1/2 and adding it to get there, and the rest is basically back substitution. So hopefully, you know, this was as basically this exact same method as it did in 0. The whole point of discussion 0 is to not introduce this matrix yet, but just to solve the system equations, like literally. But now the matrix helps provide us a system of organization so that we can consistently do this elimination method without many faults. So the next part is basically the same thing, except they already set it up for you. So I'm just going to skip that because it is basically the same thing. It's just straight Gaussian elimination, and you can see the answer key for the solution. The only difference is that you're allowed to switch. So if you have like the first one 0, well, you can eliminate from the first row because you want this top left to be equal to 1. So you just switch it with something that isn't 0. So for this example, 0, 1, 2, 2, 0, 4, 1, 2, 0, you would want to switch the second and first rows. So that's just a general tip. Another thing is that you want to always convert it to the augmented matrix. So instead of ax equals b, you just do a and then you augment it with b. That way you have the direct equations, and then you can just, you know, do the algebraic manipulations that are proven valid in Gaussian elimination. Speaking of proving that it's valid, skip to part F, which is where I'm going to prove that it is indeed a valid solution, Gaussian elimination. So remember how in part 0 we just focus on elimination, which is just multiplying and then getting rid of the variable? Well, this is what the whole point of Gaussian elimination. And why are these steps that are using Gaussian elimination adding rows, scaling rows, and row swaps? Okay, so I'm going to start with some simpler ones. Row swapping is just the same equations, you're just putting them in a different order. So they basically, it's the same system, nothing gets changed to the system. Of course, is it valid? Adding rows, well, if you have two balanced equations, well, if you add these So basically, the key for adding and scaling proofs is to treat each row as an equation, which it is. That's the whole point of Gaussian elimination. You have these variables, a linear combination of variables on the left is equal to the variable on the right, or the constant, right? So that's the whole point of the Gaussian elimination. Now, when you have the elimination, you're allowed to add. So if you have two balanced equations, which we're going to treat as balanced because that's the whole point of solving a system equation. Well, these are balanced, and then the other are balanced. Well, if you add them together, the left sides are balanced still, and the right sides are still balanced. Therefore, it's valid. Same thing for scaling, right? So I drew a little graphical representation. If square equals square, and then triangle equals triangle, well, then square plus triangle is square plus triangle. That's a valid. And then here's another visual representation, squares, and then I scale them by 2. It's still valid, right? That's how equations work. All right, and for the last one, we get a little more applied for discussion 1b. So basically, it's the same thing, right? So then we set up the equations based on the measurements. So measurements 1, you have only x1, x3 are light, and then x1, x2, x2, x4, so on and so forth. And then we get to this equation. We just do the standard matrix x1, x2, x3, x4. So x1 plus x3, it's everything else is 0. 1, 0, 1, 0. And then we go on, right? 1, 2, 1, 1, 0, 0, 2, 4, 0, 1, 0, 1, 3, 4, 0, 0, 1, 1. Yeah, and then x is just expressed as x1, x2, x3, x4, which is in the correct order. We did in the correct order, and that's the measurement vector. So for B, now we have to care about a new concept called linear dependency, which there is a separate lecture on. Basically, all you have to know is that if a system, like some information can be derived from other equations, then you are not going to get a one-to-one like unique answer. You're going to get either no answer because it's not consistent solution, or you're going to get infinite answers because it's true, but you don't have enough information to deduct any more candidates. So in this one, equation 1 plus equation 2 gives you the same equation, 1 plus 3, equations 1 and 3 give you the same information as equations 2 plus 4. Therefore, they're linearly dependent, and you can't distinguish. They're the same sets of data, essentially. So that's linear dependency. I encourage you to look at that lecture if you want to learn more. And then see, well, now you have the scale of 0.5, and that changes everything because the scale of 0.5 just allows you to essentially get a new like distribution essentially of the lights. So that is a linearly independent solution, which you'll find will result in the correct answer. So that's part C. So part 3 is some proofs. My notebook is not really the best place for that, so I'll just verbally do it. For A, it's just the concept of, so basically it's just the concept of linear dependency. If you can predict one equation from the other, well, if it's true, you already predicted it. You don't have any more information, and therefore, as long as you satisfy the other ones, which we assume has not been restricted enough, then that's infinite, because you haven't restricted it to a unique solution. But as long as it is true, then it's just infinite because you just satisfy the other equations, n-1 equations. But if it's false, then that's implying that if you satisfy the other equations, n-1, then you can't satisfy this. So therefore, the system's inconsistent. There's no solution. So for part B, it is basically the same thing, but in matrix representations. Linear dependency means you can predict it from something else. And then the physical interpretation is basically you can predict it from something else. Therefore, you do not gain any information. So if it is already the same and satisfied and consistent, then it is, it's just true. It is infinite solutions. But if it's not consistent, then therefore there's no solution. And then part C and D are proved together because D can be used to prove C. So part D is basically a proof of rank. So an easy way to prove this with literal matrix representation instead of a general linear transformation representation, we can just use the concept of Gaussian elimination, which we already proved in the last discussion as a valid method of solving for equations. Well, we just Gaussian eliminate such that there is one pivot in every column. That's what you want. But you can only have as many pivots as you have rows. That's just the general explanation. So if you have less rows and columns, then you're going to only have the row amount of pivots. And you can only have as many pivots as you have columns because there is a pivot in every column. Therefore, it only makes sense that you can have only that many pivots maximal. So if you Gaussian eliminate it and you only get the minimum amount of pivots, then that's your maximum rank. Therefore, in part C, I can apply that. If there, you can have linearly dependent independency is just how many rows or columns are linearly independent is your rank. And then I just proved that in part D. So if n is greater than m for part C, that means you have more columns and rows. Well, you cannot have more pivots than the number of rows. Therefore, the maximum amount of linearly independent vectors, which is how many pivots can you obtain, is the number of rows, which is m in this case. So I hope that was a very uh, good introduction, kind of just a review. For those of you who are previewing this course and have already taken Math 54, that's great. Otherwise, I hope this was a good introduction into kind of like why we study linear algebra.